on the new EU rules on food packaging, and when it comes especially to BPA, which is the short name for bisphenol A, and PFAS. The presentation today will be given by, if I can go to the next slide, yes, by Andreas Grabitz. He's an expert in food contact material, and the presentation will be divided in two. First, to address the new PFAS rules, and afterwards the new BPA rules. And it will basically cover what these substances are and why they are used, also why the EU is now regulating these, what are the new restrictions or a ban, and the linked obligation and the challenges for agri-food operators. And it will end with Andreas presenting a strategy and a timeline to comply with these new requirements. The presentation will last for about an hour, and we will have half an hour time for a Q&A session. So whenever you have a questions, please feel free to write it down in the chat, and we will collect them. We will try to address as many questions as possible during the live Q&A session, but rest assured that we will also collect them and answer them in a written form after the session, so everybody can have a look at it. Today's webinar is organized by the AGRINFO program. I think everybody is aware about this program that is supported by the European Union. However, the content of the presentation is not reflecting the position of the European Union. This is the short disclaimer. As you know, AGRINFO is a tool that helps monitor the European rules when it comes to agri-food linked topics, and it consolidates those rules and it tries to simplify them for key stakeholders to understand them easily. This is a snapshot of the website that you might be familiar with. Otherwise, I would invite you to have a look at it. And I would also invite you to sign up to our newsletter. There's the link here. We will put it in the chat as well. And then you can expect to receive a newsletter every 2 to 3 weeks. And it's available in English, French, Spanish, and Portuguese. Today's session will only be in English. But if you want to have live interpretation into French or into Spanish or Portuguese, you can sign up for the same session, but that will be held next week, and there will be live interpretation. And then lastly, just as a short introduction to today's topic, we will talk about food contact material. So it is a subtype of packaging that is really in contact or intended to be in contact with food. And because of this specific nature of packaging, it needs to comply with both food contact material rules and also with packaging rules. But it's important to remember that this presentation is only about substances of concern in this type of packaging, not in the food itself. This is linked to other rules, say on contaminant. And with that, I give the floor to Andreas and wish you a nice session. Thank you.
Yeah, good morning. Thanks, Axel, for your introduction. I would like to share my screen, and this is the right one. Yeah, I'm Andreas Grabitz. I'm founder and CEO of FCM Expert, a consulting company. Axel, is it sharing the right screen? I'm sorry.
Yes, it's perfect. We see it well.
It's perfect. Okay. Yeah, and I was invited by AGRINFO today to give a introduction into the new rules on bisphenol and PFAS. There's my screen, my mouse here. Okay, the basic difference between the two substances and the regulations which are in place, very recently came in place for these two substances is, Axel found this very, very nice picture, which I really love, is that we have on the right side, we have a complete ban with some very, very few exceptions. I will introduce them a bit later. But we have, in principle, we have a ban on the use of bisphenol A in any type of food contact materials. While for PFAS, we have a different rule. The rule for PFAS is not that the use is completely banned, but it is limited to a certain amount. I will explain the difference a bit later, but the fundamental concept is different. Complete ban versus a restriction for a certain chemical. Okay, if we look into the background, let me start with PFAS. PFAS is a group of chemicals which is regulated in the new EU regulation on packaging and packaging waste. This is what Axel introduced in her slide, that we have on the one side the laws which are addressing the food safety, substances which are contaminated food coming from packaging, and on the other side we have a packaging legislation which is primarily an environmental law. And the PFAS rules are established in these new PPWR. What is the abbreviation? What are PFAS? Before we go into the regulation, let's discuss what is PFAS. And actually, the problem is that PFAS is an extremely large group of chemicals. So enforcement bodies believe that there are at least 15,000 different substances which belong to PFAS. The one very, very, very big group of PFAS are polymers. And the most important one probably is Teflon. Teflon has a monomer, a building block, and this is connected to millions of other building blocks, forming really a polymeric material. And I'm rather sure you know Teflon is extremely inert. It is resistant against high temperature, against fatty food, aggressive acid. It is extremely stable and it does not migrate. It is used, for instance, for non-stick coatings in kitchen and household articles, but also in industrial food production. Such surfaces can be coated with Teflon to avoid food sticking onto the surface of the production machinery. Also in green energy, in solar cells, in windmills, you name it, Teflon is used in thousands of applications of our daily life. What is important to understand is Teflon is usually not used in food packaging, and hence it is not covered by the new legislation. So Teflon in non-packaging applications can still be used. This is no problem. It is a packaging and packaging waste regulation, not a industrial instrument or a kitchenware regulation. The second part is also polymeric, but it is different. It is a polymer which is non-PFAS. This is what you can see here. This is in white. This is a normal hydrocarbon. And here the PFAS are bound on the polymer. But the problem is that we have here some weakness. So these red bullets, they are very keen to get detached. And then substances are released from these polymers. As mentioned, completely different, and also the applications are very different. So these type of polymers are used to coat primarily paper and board to get a water and fat repellent surface for coffee to go cups, but also for others, for other water and grease proof paperboard. They are very prone to degradation and can release small PFAS molecules. Here are other examples: popcorn bags intended for microwave, or boxes for cakes and biscuits, fast food boxes which are sold in fast food restaurants, etc., etc. And here the real problem is that these substances are really found in food. This is an overview of a scientific publication, and here you can see these substances which are intentionally used in paperboard. They are found in butter, in cheese, in potatoes, in bread, and these are those small molecules which are attached to the polymer. They are not the polymer itself, but they are attached. That is important to understand. So we have Teflon as the non-stick surfaces for machinery, for pans and fries and so on. And on the other side, we have the coatings for paperboard products. And finally, we have a third application. This is again a polymer, but this is a mixed polymer. You see, this is dark and light blue. So these are different building blocks. And they are used in plastic manufacturing. So this is a typical LDPE film, and these PFAS molecules are polymer production aids. So they are used to make the polymerization or the production of the final plastic article smoother, easier, more convenient. So this is a schematic drawing of an extruder. You know, this is where plastics are melted and then there is a film blown or a bottle is produced or whatever product. And during melting the plastic, the liquid plastic passes the extruder, and these polymer production aids, these chemicals here, are used to reduce the friction within the extruder. So it makes simply the manufacturing of the articles easier. That's the intention of a polymer production aid. Specifically, they are used for polyethylene and polypropylene, which are suitable for high temperature applications like bags or pouches for baking oven applications, for microwaving, and they are added to avoid what the manufacturers call a shark shrink or a melt fracture. So the plastic manufacturers amongst us, they may know that sometimes if you do not add properly additives during the manufacturing, you get such malfunctions here. And this is what they mandatorily want to avoid. These polymers are also chemically very, very stable, but they stay inside of the plastic film. The plastic film is a packaging, and hence it is covered by the new legislation. And finally, the fourth example I want to show you is not an intentional use. It is a byproduct or a contamination which happens during packaging manufacturing. These are typical examples of a polyethylene container made from HDPE, high density polyethylene. And you know, these containers, they have a very, very poor barrier function. So gases, oxygen, but also aroma from food very quickly penetrate through the wall of these containers. So show poor barrier properties. And what happens if the barrier property is so poor is what industry calls a bottle collapse. So if you do not improve the barrier properties of these containers, then the food inside or even the oxygen from the headspace can penetrate through the bottle wall, and then the bottle is not really collapsing, but it is shrinking. So the volume gets smaller and smaller because the content goes outside. And to avoid that, industry is used to apply elemental fluorine gas. It is blown into the inner side of the bottle. So this is what we call a direct fluorination. And then we get on the inner surface, we get a layer of of bound fluorine attached or bound to the polyethylene wall. And this forms a protective layer which significantly improves the barrier properties. So here we have fluorine gas. It's not really a PFAS, but what happens is that during the direct fluorination, PFAS are formed. And here you see some measured PFAS in fluorinated HDPE. Don't care about the units here. It's just to show you that really during the direct fluorination, it happens that PFAS are formed. So we need to be aware that HDPE bottles are a potential risk to introduce PFAS into your supply chain. And last but not least, PFAS also consists of small molecules like PFOA, like PFOS, PF-hexanoic acid, and so on and so on. There are hundreds, if not thousands, of single small molecules. All of these molecules, all of these single substances, they are not used in industrial applications in food and food contact industries. You saw in my previous slides, we have the polymers, the macromolecules, they are used. The small molecules are in our applications, food and food contact materials are never used. That's very important to understand. They may occur as breakdown products or as impurities, as we have seen with the paper coating, but also with the direct fluorination here. These substances are formed as impurities or as contaminations during the process, but they are not used by intention. These substances, they are often extremely stable in the environment. They show very little degradation. And they also show a certain toxicology, while the polymers are of no toxicological relevance. The small molecules, they are. And as mentioned earlier, a US environmental health science estimated recently that there are maybe around 15,000 substances which are industrially used, which belong to PFAS. So why are the EU or also other countries, to be honest, there are more and more countries also in the United States and in India and from China, they all have already or plan to introduce restrictions on PFAS. Why is that the case? What is the reason? So actually, I do not want to go into the details of this graph, but what it shows is these stability in the environment. So substances, once released into the environment, are distributed via the air. So in the gas phase or attached to clouds or to particles, they are distributed via the water, river, but also groundwater. And when they are in these compartments, they are there for long time. So scientists partly believe that the half-life in the environment are 400 to 500 years. So we nowadays contaminate the globe for the future, and that's really the reason why the authorities tend to restrict them. Extremely persistent in the environment are found more or less all and everywhere, in remote areas, in the Arctics, in middle of the oceans, you name it. And specifically, also the smaller components are of a certain toxicology. And we trust that the PPWR, so the regulation we are looking into today, is just the first step. So the European Union also has a general chemical legislation. This is called the REACH regulation, and this is already a sign that this will follow up and gives a more generic restriction for PFAS also for other products than food packaging. Okay, if we look into the new regulation, as mentioned, this is 2025/40. This is the PPWR, the new regulation on packaging and packaging waste. And in Article 5, it says, and that's the very first, very important information, the regulation or the restriction starts to be in place on 12th of August next year. So on 12th of August next year, any packaging which will be placed on shelf in the EU must contain less than these three concentration. 25 ppb for any single substances. You remember PFOA, PFOS, and so on. For the sum of all these compounds, the concentration limit is 25 ppb, and for the total fluorine, the limit is 50 ppm. I will explain that a bit more in detail, what exactly this means. So we are talking about, or the EU is restricting the content in the packaging. That's very important to differentiate the content from the migration. You know, when we talk about BPA, when we talk about phthalates, we talk about the migration. So how much is moving from the packaging into the food? So we are not interested what is in the packaging. We are just interested in what is transferred, what ends up in food, and what will be eaten by the consumers. So the specific migration, we know a lot of substances like BPA, like DEHP, where we have a specific migration limit. And the basic question of specific migration is how much is consumed, is eaten by the consumer, and is this a hazard for the safety of the consumer, for the health of the consumer? Here in PFAS, we have a completely new approach. The total amount present in the packaging is restricted. We do not, or the EU legislation is not discussing the health hazard for the consumer, but it is an environmental legislation. So the EU does not want to get PFAS present in packaging and then at the end of the life cycle end up in the environment. That's very, very important to distinguish. So coming back again, we have two limits. The one is on the single substances and the other is on total fluorine. To look into the difference, we need to have a very, very tiny piece of analytics. So when we look for a single substance, we take a very sophisticated instrumentation that can be a gas chromatograph or an HPLC, whatever. It doesn't really matter. We need an instrumentation which can detect all of these different substances. And we get such nice chromatograms where all of these single substances, you remember we saw them earlier, PFOA, PFNA, and also sulfonic acids, and so on. All of these different compounds, which are either generated as impurities, you remember the direct fluorination, or which are released from the paperboard, right? So they are separated by the instrumentation. And what we now need to do, what the instrumentation needs to do, is that we identify what is that. So the instrumentation does not know from itself that this is PFOA. We need to train the instrumentation. We need to show the instrument that is PFOA. And the next one is PFNA and HEXA and so on. So we need standards. We need analytical standards which we can purchase, which we can buy, inject into the machine and say that is PFOA. But we also need to tell them or to train the instrument, how much is it? So the instrument does not know by itself that this peak is equal to 1 milligram, for instance. We need to train it. We need to show the machine 1 milligram of PFOA and tell it, okay, if the peak is that large, this means it is 1 ppm. And then the instrument can calculate an unknown sample with regards to the concentration. So the analytical standards are absolutely mandatory. We can't analyze PFAS without analytical standards. And the problem is that currently we believe around 500 to 600 substances are available as analytical standards, but we learned earlier we have around 15,000 chemicals. That's a huge problem. We have a large gap because analytical standards are not available. And hence, all of these substances can't be analyzed. That's a large problem. And most of the laboratories don't even have all of the 600 substances. They have probably 100. And most labs offer between 30 and 60 substances out of 15,000. So we really have a very, very small picture of the whole situation. And we have a tiny overlap of the most critical substances like PFOA or PFOS, but beyond that, the variations from one lab to the other are very, very large. And the consequence is that the results which you receive from one lab to the other are very poorly or even not comparable at all. So comparability of analytics is a really, really huge issue. So I like this picture of a lighter, and the lighter looks into the darkness, and within the light produced by the lighter, we see a couple of substances. 30, 40, 50, 60 substances, but we have a dark matter surrounding that with a lot of question marks, with unknown substances, which the light can't see because we don't have a proper instrumentation to have light all and everywhere. We just can focus on these substances where analytical standards are commercially available. Or show this in another graph. We have here the 30 to 60 substances or even 100 substances where we can target analysis, where we have an instrumentation to look for PFOA, PFOS, PFHexa, and so on. But there is a huge bubble of more than 15,000 substances, and we have no clue what is all of that green here outside of the red bubble. And what is even worse is that there are also inorganic substances, salts, right? Fluorine salts. There are some examples which are used in industry, and all of that together forms the total fluorine. And the total fluorine, that is what is regulated in PPWR. And these salts can be, for instance, calcium fluoride as a filler in paper, a very common filler, where we have partly 15 to 20% of the total weight of a paper forms calcium fluoride. Or in plastic manufacturing, if you have a plastic bottle or a plastic tray which is not transparent, the transparent films do not have a filler. But if this is not transparent, if this is colored, industry often use a filler, and that can be talcum. And talcum contains a certain amount of fluorine. And that is really a huge, huge problem. So for the total fluorine, what the analytics is doing, what the laboratories are doing, is they take a sample, let's say of a plastic film, of a paper board, or even of an environmental sample or a food stuff, right? They are placed in an introduction inlet, let's say. This is a small pan, and then it is placed in an oven, and it is heated to very, very high temperature, 900,000 degrees, or sometimes even a bit more. And all of the sample of the plastic film of the paperboard will be burned. It will be incinerated, and all of the exhaust gases, they are bubbled through a water bath, and the fluorine from the PFAS, so the elemental fluoride atoms, they are absorbed by the water, and then they are dissolved in the water bath. And from the water bath, we can run what is called an ion chromatography and get such a much easier picture. And here the first one is the smallest. This is the fluoride. This is chlorine. This is bromine. So a very, very simple chromatogram. So what we do here, to take again my lighter picture, is we turn on the light and we only look for fluorine. We do not consider, was this a small molecule? Was this a large molecule? Was this a toxic substance or a harmless substance? Was this a monomer, a small molecule, or even a polymer like Teflon? We don't care. We just look for fluorine in sum, for the completeness of the fluorinated molecules. And this is what we call the total fluorine, as mentioned earlier. So one of the critical points here is that depending on the temperature and the temperature gradient, the results can significantly differ. So this step here is really the critical point, the combustion step, where we burn or where we incinerate the sample. And this brings me to the challenges. So when we go for the total fluorine analysis, we have partly the problem that we can have an over or an underestimation when there are fluorine salts in the sample. then this can lead to an over or an underestimation. And the major problem is really that we don't have a harmonized and a standardized method right now. Every laboratory uses its own methodology. They are usually validated, sometimes accredited, but they are not harmonized from one laboratory to the other. So we have a high uncertainty with regards to the reliability of the results, and only very limited number of labs worldwide which can offer this service. And the authorities are hardly working at the moment on the standardization of this methodology to overcome that problem, because you really can't compare the results from one laboratory to the other, as it very, very strongly depend on the methodology the laboratory is applying. And the single substance analysis, just to repeat that, we have very different list of PFAS substances covered by the different laboratories, and therefore the results are not comparable from one lab to the other. And specifically with regards to the instrumentation, this is a very, very expensive instrumentation, and the capabilities in most of the supplying countries are very limited because the instrumentation is so highly sophisticated and consequently also very, very expensive. That is one of the drawbacks of all of these analyses. Okay, what can be your PFAS strategy? As an introduction, we hoped that prior to this webinar today, the EU guidance document is already or would already be published, but this is unfortunately not the case. EU Commission has announced that they will publish a guidance document with regards to the PFAS restriction to support industry how to comply with the new laws. AGRINFO will provide also a technical guidance for PFAS, which will be published later this year, but before Christmas. And we will also prepare an update next year when the guidance is finally published, and promised if you are getting the newsletter of AGRINFO, you will also get the update when the guidance document will be available. So all of that, what I tell now, is to be taken with a bit care, because it is subject to possible changes when the guidance document is published next year. So the first step I would strongly recommend is check with all of your packaging suppliers that PFAS is not intentionally used. I know I mentioned that in the first slides. It is not a ban, so industry are allowed to use PFAS as long as they are in compliance with the limits in the PPWR. But the better solution is don't use PFAS at all. Then you are safe. It is not in there. Don't forget materials like adhesives, printing inks, labels, closures. So all components should be checked that there is no PFAS intentionally used. Then you can be already on the rather safe side that there is also no PFAS present in your material. Actually, there are two materials where you should be take a bit more attention. One is paper and board with a water and fat repellent property, as well as polyethylene and polypropylene for high temperature, like microwaving or baking oven suitable materials. Here, I would recommend go for a total organic fluorine by an external laboratory. And to be honest, at the moment, I must recommend you to select a laboratory which is either located in the United States or in Europe. I believe that most of the developing countries nowadays do not have really fully validated total fluorine analysis in-house. And make sure if you are asking a lab for analysis that they have at least fully validated methods. Prefer methods which are accredited by the laboratories. Ask them, is the method accredited? Is this validated? And please provide me a validation or an accreditation document. Okay, that's about PFAS. Let me switch to the second one, BPA. I think most of you have heard already about BPA. This was regulated lately last year, so close to Christmas 2024. The EU has, to a certain extent, surprised us with a new rule on bisphenol A. Where is bisphenol A used? So the first and I think the most important application is the inner coating of metal cans. You know, such a metal can here has a coating on the inner side to protect the metal against the aggressive food inside. Otherwise, the metal can roast, and then metals are released into the food in very high amount, and we want to avoid that. So the metals are lacquered; they are coated on the inner side, and these the lacquer with the best performance and unfortunately also with the lowest price are epoxy resins. And these epoxy resins, they are made, or there is bisphenol A is one of the starting substances. And if you use them, they are migrating. They are transferred into food depending on the temperature. You see this here. So that is really a crucial point, that BPA, if it is used in the can coatings, then it also migrates. This is another study showing exactly the same picture. Another application are polycarbonates. Polycarbonate is a certain plastic type. It is a plastic which is very hard, which is highly transparent, so it looks like glass. It has very common optical properties like glass. It is extremely stable, so it is a preferred material, or it was, to be honest, a preferred material where you need this high transparency of a plastic material. Here, polycarbonate is unbeaten. But again, the problem is that BPA is released in very, very small amounts. That's true. It is very, very tiny, but BPA is released into the foodstuff, and therefore nowadays all of these water bottles or the baby feeding bottles, BPA is more and more phased out. You know, in the baby feeding bottle, it is even banned since around 10, 12 years because of the problem of BPA migrating from polycarbonates. So, you know, in food packaging, when it really comes to packaging, which is sold to the customer, in the consumers, in the retailers, polycarbonate is very, very little. So I can't really remember a packaging made from polycarbonate. These are more kitchenware articles like these bottles. But a third application is in printing inks. So there are printing inks which contain what is called an epoxy acrylate. And this epoxy acrylate is then present in around 15 to 20%. And this is true for what we call an UV curing printing ink. UV curing is a specific technology how to dry, how to cure a printing ink. And this is not by applying some heat or removing solvent by higher temperatures, but this is a curing process initiated by a UV flash. And the UV flash initiates a polymerization of the solvents of an UV curing ink. And if this is made with an epoxy acrylate, then we have the problem with the BPA. And therefore, you need to be a bit careful when you use these UV curing printing inks. Again, the question, why is the EU Commission regulating that? And the reason here is completely different. The BPA is also present out there in the environment, but the main issue here is a health issue. So BPA is what we call an endocrine disruptor. An endocrine disruptor is a chemical that mimics the behavior of a hormone. A hormone, and here you see an example, probably the most important or the best known, this is estrogen. the hormone which is responsible for most of the processes in female bodies. And here you see bisphenol A. And this structure here at the very left corner is very, very similar. And this similarity in the chemical structure results that the estrogen and the BPA can be bound, can dock onto the same receptors. These receptors then initiate something like growing of breasts in young female, or the ovulation and so on. So all of these hormone activities in female bodies are initiated by binding estrogen onto some receptors. And BPA has the possibility, has the chemical structure to dock onto the same receptor than estrogen. And consequently, it induces effects like estrogen do. And that is what I showed earlier here, breast development and so on, all of these effects. They are also initiated by bisphenol A, by endocrine disruptors. And the new regulation, which was published end of last year, bans the intentional use of bisphenol A and also other hazardous bisphenols. So not also BPA, but other very similar molecules which have hazardous properties. And the ban is applicable for adhesives, rubbers, ion exchange resins, plastics, printing inks, silicons, and varnishes and coatings. So for the vast majority of raw materials in packaging industry. But what you do not see here is that there is no strict BPA ban in paper and board. So there are, in certain countries, there are limitations, mainly with regards to the release into the food. But this EU-wide ban of BPA is not applicable to paper and board. Nevertheless, the intentional use of BPA in paper and board is, of course, also not advisable, because we know these hormonal effects, these endocrine properties are there. And therefore, BPA should, of course, also not be used by intention in paper and board. But it is rather clear, and we should understand, the restriction does not apply to paper and board, but only to plastics, printing inks, and so on and so on. So the first question, of course, is what is a hazardous bisphenol, right? The regulation restricts or bans the use of BPA and other hazardous bisphenols. Actually, the regulation references what we call the CLP regulation. CLP is another EU law which regulates the labeling of hazardous chemicals. And we have 4 categories of hazardous chemicals which are under the definition of being hazardous in the BPA regulation. First is a mutagenic compound, so it means that the chemical damages the human DNA. Carcinogen means it causes cancer. Toxic to reproduction, harmful to unborn babies or mother's womb, and endocrine disruptors, so which mimics the hormone in human bodies. So if a substance has one of these 4 properties and is a bisphenol, then it is considered being hazardous. I have looked for you into the CLP regulation, and currently there are five substances which are bisphenols and which are either mutagenic, carcinogenic, toxic to reproduction, or have endocrine properties. These are bisphenol A, bisphenol S, and bisphenol AF. These 3 are the most relevant. So they are really used in production of food packaging, like can coatings, printing inks, and so on, right? The other 2 here, these ones here, they have other applications, and this is a flame retardant. So this is used in textiles and so on, and in furnishes and so, but not in food packaging. So we don't need to take care of that. BPA, BPS, and AF. They are defined as bisphenol and as being hazardous. There are two more which are currently under very critical observation because they have the same properties, but they are currently not listed in the CLP regulation, but we expect that they will be listed in the near future. This is bisphenol B and bisphenol F. So if one of you will start an analysis controlling bisphenols, then you should consider these 5 substances: AS, AF, bisphenol B, and bisphenol F. That is, these 5 substances are, 3 are really covered by the law, and 2 are under very critical observations. So what exactly is the regulation currently prohibiting? So there are 3 bans. The first is that bisphenol A, the intentional use of bisphenol A, is not allowed anymore, with some transitional period. I will show you the entry into force at the very end. So it is not allowed to use bisphenol A intentionally in food packaging. It is also not allowed to use other hazardous bisphenols. Currently, this is mainly BPS and BPAF. Also, we have some derogations I will show you a bit later. But BPA is prohibited, and also other hazardous bisphenols are prohibited. And if you are using another bisphenol, like BPF or BPB or bisphenol M, so there are a lot of other bisphenols which are used in the market for food packaging, then bisphenol A must not be detectable. Then you must control, is in your final packaging, is BPA detectable? And the answer must be no, must not be detectable. Okay, we have 2 derogations. I showed you here 2 derogations from the complete ban. These are shown here. The first is epoxy resins, which are applied to large tanks in food production with a capacity of more than 1,000 liters. So only very, very large tanks. And the second exemption is polysulfone filter membranes, which are often used in the food production factories, but these are not packaging. So it does not concern packaging or food you are packaging in your country and then importing in the EU, because these 2 exemptions are not packaging materials. They are production instrumentation, let's say, right? So this is not really relevant for you. You must take care of the packaging you are using to export the food into the European Union. Okay, there are not only prohibitions, but there are also obligations. And the most relevant, the most important obligation from the new EU law is that you need to provide a declaration of conformity. The declaration of conformity is shown in Annex 3 of the regulation. And for most of you which are using or which are selling or importing plastic packaging into the EU, this is not really new. We know that from the plastic regulation 10/2011. There we also need a declaration of conformity for any plastic packaging imported into the EU. And the content is rather comparable. So there is nothing really new. But what is new, this is shown here in bold and also here in red. First time ever, you must include a phone number or an email address your customer can use to contact you if they have questions, if they have some comments. Then they must have the contact data, current contact data on the declaration of compliance. That's new. You must take care of that. Secondly, the regulation says that you must provide a list of any bisphenol or bisphenol derivatives which are used in the manufacture of food or food contact material. Even in the case none is used, you must confirm that none is used. Not only leave it empty, but you must confirm there are no bisphenols or bisphenol derivatives used in these type of food packaging. And finally, clause number 6 says that you must confirm compliance with this regulation. This means this regulation has the name 2024/3190. So you must confirm that this regulation is considered and the material complies with 2024/3190. That must be written on the declaration of compliance. And actually, you can imagine this is something an enforcement, the authorities, the control labs very easily can look through the declaration of compliance and see, is this number mentioned here? They can even use artificial intelligence to control that, and they control declarations of compliances automatically, very, very quickly. And if they do not find, they complain. And this is what we already see in the EU, that the enforcement, the authorities control the declaration of compliance. They do not measure bisphenol A, but they control the declaration of compliance and look, are the formalisms, which you can see on this screen, are they fulfilled or not? Right. The regulation also defines analytical control. This is mentioned in article number 9. Method to control the content and the release. You remember the one was what is in the packaging, and the second is what is migrating from packaging into food. And article 9 says that any method to control the content in the packaging and the migration into food must have a detection limit, a very, very, very low detection limit of 1 microgram per kilogram. What is 1 ppb? So there must be less than 1 ppb content and also less than 1 ppb migration of bisphenol A into the food. And that is really a huge problem, that this identical, extremely low limit for the specific migration and for the total content causes a lot of problems. But what is also very, very important to understand, analytical control is needed in 2 cases. If the packaging is manufactured with a non-hazardous, you remember the hazardous are forbidden, they are prohibited. You are not allowed to use a hazardous bisphenol. But with a non-hazardous bisphenol, then you must control the residual BPA content. So if you get a documentation, you ask the suppliers, and the supplier tells you, yes, in my product I have bisphenol M or bisphenol B or any non-hazardous bisphenol. Then you need to go to a laboratory controlling the bisphenol A level and have a documentation that the bisphenol A level is lower than 1 ppb in the packaging material. It is the content, right? But this is only required if you ask the suppliers, do you use a bisphenol, a hazardous bisphenol or another bisphenol? And if they confirm, yes, I do. If you have confirmation in the supply chain that no bisphenol or bisphenol derivative is used, there is no need for analytical measurements. The second one is if your material is based on an exemption. You remember these were large tanks with more than 1,000 liters and the polysulfone membrane, then a migration has to be performed. As mentioned, you are not based in the EU, it is not relevant for you. But what is really important to understand, analytical control is by the legislation, by the law, is not needed for a food packaging when you have the confirmation that bisphenols are not used by intention. If the suppliers confirms we do not intentionally use bisphenols, any bisphenols, then there is no need for an analytical control. And what is also very important, this includes contaminations. So we do not need to take care, is there a ppb or 2 or 3 ppb contamination in a packaging material? It is about the intentional use that in a packaging manufacturer, that the packaging manufacturer actively introduces a bisphenol into the packaging. If this is not the case, then you are out of scope of the regulation and you do not need to control that. Only the intentional use is forbidden. Unintentional contaminations, e.g., for instance, from recycling processes, are in principle allowed. So no analytical control in these cases. So only in very, very small exemptions, analytical control is really needed. So what are the challenges? We have an extremely low detection limit required by the new law with a detection limit of 1 ppb. It is very, very challenging to find laboratories which can even offer these extremely low limit. 1 ppb is in the European Union, I would say 1 or 2 years ago, most laboratories offered 1 ppm, 1 milligram per kilogram as detection limit. Nowadays, it must be 1 ppb, which is a factor of 1,000 lower. And I believe it will be really challenging outside of the EU to find a laboratory covering this very, very low detection limit. We have a high risk of false positive results, either by contaminating the sample during the transportation. So if you send a sample to a laboratory, you must be really sure that it is packed properly in at least a double layer of aluminum foil to avoid that the transportation, the cardboard, and so on, that BPA is migrating from there into your into your sample. That's really a critical point when we go down to a 1 ppb detection limit. And also in the laboratories. So polycarbonates are very, very commonly used in a lot of lab instrumentation. So laboratories completely need to redesign their laboratories to phase out polycarbonates in their laboratories. That's a huge, huge challenge. So we fear that we will have in the next 1 to 3 years a lot of complaints of finding positive BPA results, which are false positives, which are not really BPA in the material, but contaminations from elsewhere. That is really, really a huge problem. Okay, I promised to show you the timeline. So the regulation is already in place, but you can place empty packaging onto the market until 20th of July next year. So currently, nothing has changed. I know customers are already asking and they want to be compliant with the new regulation, but at the moment it is rather clear nothing has changed until July of next year. In January of 2028. Sorry, so in January 2028, we have an extended transitional period, right? So here, as from July next year, the use of BPA will be banned. This can be used for fruits and vegetables, and also for fish and fish products, and also for lacquers applied on the outer side of cans. BPA may be used until 20th of January 2028, but only for these few exemptions here. For empty packaging, for all other applications, the transitional period ends in July of next year. When you have brought these products, these empty packaging into the market, the food company, this may be also you filling food into the can, we have 1 year of additional transitional time. So the empty packaging for non-fruit and vegetables and non-fishery products, which were sold before 20th of July 2026, can be filled until 20th of July 2027. And then again, we have unlimited transitional or approval to sell any food on stock until the exhaust of the stock. So if this is filled before ending 1 year after the transitional period, then you are allowed to sell that without any restriction. Right, so try to finalize and try to conclude that. So we have addressed today two really huge new regulations in the EU, PFAS and BPA. The PFAS is a limit on the use. So it is not completely banned, but we have some limitations in the law, while for BPA, we have a general ban with some very limited exemptions. Make sure that the suppliers do not use PFAS by intention anymore. A strong recommendations. For the plastics, for high temperature, and for paper and board, which is fat and grease and water repellent, go for a total fluoride analysis with an accredited lab and work throughout this complete supply chain, all other types of packaging, to convince customer that an absence declaration is sufficient. If we start to analyze PFAS in all and every food packaging material, we will never come across with that, because you all use so many different variations of food packaging that nobody can afford testing all of these variations for PFAS content. Okay, in the BPA, the world is a bit easier, because it is, on the one side, it is a general ban, but it is a general ban on the intentional use. So the first and most important step is that you need to ask your suppliers that BPA and any other bisphenol is not used by intention. If you get confirmation, that will be sufficient. And if a BPA analysis is needed, please make sure that you choose a lab which has a certain experience with these extremely low limits, and properly, intensively discuss how to avoid contaminations during the transportation of the sample. So if this is a lab which is based in Europe or in the United States, or maybe in Asia, somewhere in Asia, go into the conversation with the lab, talk to them and ask them, what is your experience? How can we avoid contamination? Give us advice how to properly ship samples to your laboratories. Right, having that said, I would like to thank you very much for your attention. And I have seen already that there are a couple of questions in the chat box, and I hope that we have sufficient time to answer all of them.
Thank you very much, Andreas. It's been a great presentation, very instructive, and I think that it's been instructive to most of our audience. I see many people clapping, so thank you for the positive feedback.
Wow, thank you very much.